In a single-phase system that uses two hot wires, which are the black conductors, to power fluorescent lights, it's not unusual to see 120 volts appear on the neutral wire, which is the white conductor, when the circuit is disconnected. This phenomenon is primarily due to the way fluorescent lights operate. They use a ballast to control the current flow, and this ballast introduces a characteristic called inductive reactance. When the circuit is open, the inductive reactance causes the current to lag behind the voltage, creating a phase shift. This phase shift results in a slight voltage increase on the neutral conductor, bringing us up to 120 volts. Now, when those disconnected fluorescent light wires are connected to the neutral bar, the 120 volts backfeed from the neutral wire finds a path to ground through the ground wire connected to that neutral bar. This effectively creates 120 volts on the neutral bar itself. But why doesn't this backfeed through the white wire cause other circuits to trip their breakers, even if they're on different phases? The answer lies in the magnitude of the backfeed current. It's actually very small. This is because of the high impedance presented by the inductive reactance in the ballast of the fluorescent lights. The small current that flows through the white wire is not large enough to exceed the trip threshold of the other breakers. While single-phase systems generally strive for balanced loads, the presence of fluorescent lights with their inductive loads can introduce a slight imbalance. However, this imbalance is typically not significant enough to cause breakers to trip on other circuits. It's important to understand the behavior of multi-wire circuits as well. These circuits, often 120/240 volts configurations, have two hot wires, typically black and red, and a shared neutral wire, white. The potential for unbalanced loads exists in these circuits. If the loads connected to the black and red wires are not balanced, the neutral wire will carry the difference in current. This can lead to overheating and possibly circuit failure. Firstly, understand that inductive reactance is the opposition to the change of current flow in an alternating current AC circuit. It is caused by inductors, such as the ballast in fluorescent lights, and is measured in ohms. The higher the frequency of the AC current, the greater the inductive reactance. Secondly, impedance is the total opposition to current flow in an AC circuit. It includes resistance and reactance and is also measured in ohms. Thirdly, a phase shift occurs when the voltage and current in an AC circuit are not in sync. This can be caused by inductive reactance or capacitive reactance. In the case of fluorescent lights, the inductive reactance of the ballast causes the current to lag behind the voltage. Fourthly, unbalanced loads occur when the current flow through each leg of a multi-wire circuit is not equal. This can be caused by connecting different amounts of load to each leg. Unbalanced loads can cause the neutral wire to overheat and potentially create a fire hazard. Fifthly, multi-wire circuits are commonly used to provide both 120 volts and 240 volts power. They consist of two hot wires, a neutral wire, and a ground wire. The voltage between each hot wire and the neutral wire is 120 volts, and the voltage between the two hot wires is 240 volts. Sixthly, grounding the neutral bar in a subpole can create a parallel path for neutral current. This can cause current to flow through the ground wire, which is not designed to carry current. This can create a shock hazard and can also interfere with the operation of sensitive electronic equipment. Seventhly, the National Electrical Code (NEC) requires that the neutral bar in a subpanel be isolated from the ground. This is to prevent the flow of neutral current through the ground wire. Eighthly, when troubleshooting electrical problems, it is important to use a multimeter to measure voltage, current, and resistance. This can help you to identify the source of the problem and to determine the best way to fix it. Ninthly, always disconnect power before working on any electrical circuit. This will help to prevent electric shock. Tenthly, if you are not comfortable working with electricity, hire a qualified electrician. Electricity can be dangerous, and it is important to take precautions to protect yourself. Now let's consider the case of a 20 amp breaker. According to NEC Table 310.15, B16, a 12 American wire gauge, Og copper conductor with THHN insulation is typically rated for 20 amps at 75 degrees Celsius, which is a common temperature rating for terminations. Therefore, using a 12 AWG wire on a 20 amp breaker is generally acceptable under normal circumstances. However, there are several factors to consider to ensure compliance with the NEC and safe operation. Firstly, the specific application and installation conditions can affect the ampacity of the wire. Factors such as ambient temperature, the number of current-carrying conductors in a raceway or cable, and the type of load can require adjustments to the ampacity rating. These adjustments are outlined in NEC Article 310. Secondly, NEC Section 240.4. D provides rules for the protection of conductors. This section generally prohibits using overcurrent protection, such as a 20 amp breaker, on conductors rated less than 15 amps, such as 14 AWG copper wire, unless specific exceptions apply. However, 12 AWG wire, rated for 20 amps, is acceptable for use with a 20 amp breaker. Thirdly, the terminals on the breaker and the equipment to which the wire is connected must be rated for the size of the wire being used. Using a wire that is too large for the terminal can result in a loose connection, which can cause overheating and arcing. Fourthly, it's crucial to ensure that all connections are properly tightened and that the wire is in good condition without any damage to the insulation. Fifthly, some local codes may have stricter requirements than the NEC, so it's important to check with the local electrical inspector to ensure compliance. Sixthly, if the load is continuous, which is defined as a load that operates for 3 hours or more at a time, the overcurrent protection should not exceed 80% of the conductor's ampacity. In this case, a 20 amp breaker should not be used with a 12 AWG wire if the load is continuous and exceeds 16 amps. Seventhly, using the correct type of wire for the application is also important. THHN wire is commonly used for general-purpose wiring in dry locations, but other types of wire may be required for specific applications, such as wet locations or high-temperature environments. Eighthly, the length of the wire run can also affect the voltage drop. If the wire run is too long, the voltage at the load may be too low, which can cause equipment to malfunction. The NEC provides guidelines for calculating voltage drop, and it's important to ensure that the voltage drop does not exceed 5% of the source voltage. Ninthly, it's always a good practice to consult with a qualified electrician if you have any questions or concerns about the proper wiring methods. Electricity can be dangerous, and it's important to ensure that all work is performed safely and in accordance with the NEC and local codes. Tenthly, consider the derating factors that may apply. If multiple current-carrying conductors are bundled together, their ampacity must be derated according to NEC Table 310.15. B3. This is to prevent overheating of the conductors. Now let's talk about the neutral wire carrying current. In a properly wired single-phase circuit, the neutral wire should only carry current when there is an imbalance between the loads and the hot wires. However, there are several reasons why a neutral wire might carry current even when the loads appear to be balanced. Firstly, harmonic currents can cause the neutral wire to carry current even when the loads are balanced. Harmonic currents are multiples of the fundamental frequency of the AC power, which is typically 60 Hz. These currents are produced by nonlinear loads, such as electronic devices and fluorescent lights. Secondly, shared neutral wires can cause current to flow through the neutral wire even when the loads are balanced. This is because the neutral wire is shared between multiple circuits, and the current from each circuit can combine in the neutral wire. Thirdly, ground faults can cause current to flow through the neutral wire. A ground fault occurs when a hot wire comes into contact with a grounded surface, such as a metal enclosure. This can cause a large amount of current to flow through the neutral wire and the ground wire. Fourthly, improper wiring can cause current to flow through the neutral wire. For example, if the neutral wire is not properly connected to the neutral bus in the electrical panel, current may flow through the ground wire instead. Fifthly, unbalanced voltage can cause current to flow through the neutral wire. This can occur if the voltage on one leg of the circuit is higher than the voltage on the other leg. Sixthly, electromagnetic interference (ME) can induce current in the neutral wire. EMI is caused by electrical noise from nearby equipment, such as motors and transformers. Seventhly, capacitive coupling can cause current to flow through the neutral wire. Capacitive coupling occurs when two conductors are close together, and an AC voltage is applied to one of the conductors. This can cause a small amount of current to flow through the other conductor. Eighthly, inductive coupling can cause current to flow through the neutral wire. Inductive coupling occurs when two conductors are close together, and an AC current flows through one of the conductors. This can cause a small amount of current to flow through the other conductor. Ninthly, neutral to ground faults can cause current to flow through the neutral wire. A neutral to ground fault occurs when the neutral wire comes into contact with a grounded surface. This can cause a large amount of current to flow through the neutral wire and the ground wire. Tenthly, high impedance connections can cause current to flow through the neutral wire. A high impedance connection is a connection that has a high resistance to current flow. This can cause current to flow through other paths, such as the ground wire. Now, let's consider common wiring mistakes. Firstly, failing to properly tighten connections is a common wiring mistake. Loose connections can cause overheating and arcing, which can lead to fires. Secondly, using the wrong size wire is a common wiring mistake. Using wire that is too small can cause overheating and voltage drop, while using wire that is too large can make it difficult to make connections. Thirdly, mixing up the hot, neutral, and ground wires is a common wiring mistake. This can create a shock hazard and can also damage equipment. Fourthly, overloading circuits is a common wiring mistake. Overloading a circuit can cause the breaker to trip and can also damage the wiring. Fifthly, using damaged or frayed wires is a common wiring mistake. Damaged wires can create a shock hazard and can also cause fires. Sixthly, ignoring local codes and regulations is a common wiring mistake. Local codes and regulations are in place to ensure the safety of electrical installations. Seventhly, failing to properly ground equipment is a common wiring mistake. Grounding equipment helps to protect against electric shock. Eighthly, making connections outside of junction boxes is a common wiring mistake. Junction boxes are designed to protect connections and prevent them from coming into contact with flammable materials. Ninthly, running wires through walls without protection is a common wiring mistake. Wires that are run through walls should be protected by conduit or cable. Tenthly, working on live circuits is a common wiring mistake. Always disconnect power before working on any electrical circuit. Understanding these basic concepts is essential for anyone working with electrical systems. Proper wiring techniques, adherence to safety protocols, and a thorough understanding of the NEC are crucial for ensuring the safe and reliable operation of electrical equipment.